Hello, everyone. My name is Yi Zhao, a PhD candidate from the University of Hong Kong. Today, I'm going to introduce you our paper, REMOT, a hardware-software architecture for attention-guided multi-object checking with dynamic vision sensors on FPGA. In this presentation, I'm about to show you some interesting opportunities and challenges in processing events from dynamic vision sensors, and how we build the hardware-software architecture based on the concept of attention. Finally, I will show you some implementation and results of our framework. So first, what is dynamic vision sensors? Dynamic vision sensors, sometimes people call them event cameras. They asynchronously measure per pixel brightness changes and output a stream of events that encode the location, time, and sign of brightness changes. Here on the top side, we see a video captured by conventional frame-based camera. And each frame are sampled at a fixed time interval, known as frame per second. However, for event camera, it only outputs event whenever there is a brightness change. And here in this video, we see that we accumulated events in the fixed time interval and generated a video like a frame by plotting the events in the original 2D space. We can see that the event camera's output are highly sparse. And here, another example is that when the stars are not moving with this time interval, there are actually fewer events because there's fewer change. We, as the hardware designers, may ask the question, what's the opportunities and challenges in hardware processing of events? Well, the first one opportunities is that event camera are highly sparse and low power, like we have just seen in the last slides. However, event camera is also asynchronous, which means that the data rate can change dynamically. Here we show a diagram showing that the data rate of the event camera is changing as the dynamic activity of the scene. And here is an table of statistics of our data sets. We have 3 data sets, and all the average event data rates are less than 1 mega event per second. However, the peak event data rates can be as high as 2 mega event per second. But usually, for commercial event camera, the events are time-stamped in microsecond. And if you want to design a system that can process events in 1 mega event per second, and assuming that your FPGA hardware runs at 200 megahertz, by simple calculation, you can find out that you need 200 cycles to process each event. To be more specifically, for any non-pipeline operations, which is a very challenging hardware problem. So how can we tackle these challenges and also leverage the sparsity and low power of the event camera? Well, in this work, we propose a hardware-software architecture based on the concept of attention. The motivation is that the events generated by moving objects are sparse and also correlatives. Here we show a picture that only a few small areas in the scene that has events. So we want that a checker to only pay attention to small areas of the small region of attention. We call them ROA. And we also want our checker to update its region of attention as the object moves, and also collect the events generated by the objects. We call this magical checker an attention unit. Here shows how the attention unit works. The AU will use an attention map to record current region of attention. And whenever a new event falls outside the region of attention, the AU will consider it not interested and just ignore these new events. However, if the new event falls within the region of attention, the AU will consider it interest and expand the attention on the surrounding D by D area. Also, we want our AU to update its region of attention as the object moves. So we need to additionally introduce a mechanism to shrink and forget the old attention. Here's where this active event FIFO comes in. When the new event is collected by the attention unit, it will be pushed into this active event FIFO. And when the FIFO is full, the old events will be popped out. And also they will shrink the attention on the surrounding D by D area. So in this way, the region of attention can be adapted as the object moves. So now we have some basic idea of what is attention unit. You may also ask the question that how can we ensure that these attention units are checking properly? Well, that's also the reason why we decompose our framework into hardware and software. On the hardware side, we process each event in microsecond level by doing the expand and shrink of the attention map. While in the software side, we run high-level vision decision algorithm that may decide to merge two AU into one AU if they are checking the same objects, or split one AU into several AU for them to check different objects. So how to implement this kind of hardware software architecture? Well, on FPGA, we implement the parallel AU on the programmer logic. You will directly take the event stream as inputs and broadcast the events to all the AUs and ask them, are you interested in this event? Which means that is this event falls within your region of attention? If yes, then those AU will take the events and expand or shrink their attention map. If no one is interested, the new event will go to next free hardware AU. And also we provide interface for the hardware to return the status to the software that runs on the processing system. The software will calculate the bounding box and velocity based on this information, and may also decide to merge or split certain AU. So in turn, we provide interface for the software to control the status of the AU. Also, we claim that the remote architecture is a highly flexible architecture. To show this point, we propose different AU implementation, the full attention map, hash A map, and FIFO only implementation. And also on the software side, we implement some modular different merge and or split algorithm to show that our architecture is highly flexible. For the first AU implementation, we use a full weight times height storage to record the current attention map. And it's easy to see that it does not consider the sparsity of the event data, but it's a straightforward implementation. And the interest of operation is defined as whether this position XY has the attention map larger than 0. And the expand and shrink operation is modeled as plus and -1 on the D by D area centered at XY. And also the push and pop active event FIFO actions. So in the second implementation, hash A map, we will leverage the sparsity in the attention map. We use a hash table to store the attention map. For example, here for the point x, y with the value 50, for these non-zero points, we unravel the index to be the key of this key value pairs. And we do the hashing on the key to obtain the index of these non-zero points. For example, here is 170. And we store these key value pairs in the hash table entry. So now the interest operation is changed to finding or querying the corresponding key value pairs at the XY position with the value larger than 0. And then explain or shrink and also the push and pop active FIFO are similar with the previous full attention map implementation. So the difference is now we are using a hash table to store the sparse attention map. In the last implementation, FIFO only, we actually use an equivalent model of the AU without explicitly use the attention map. We only use the FIFO. So the interest operation is defined by traversing all the collected active events in the active event FIFO to find out whether there's the closed event within the D by D area. So the expand or shrink operation now becomes only the push and pop on the active event FIFO. However, now the performance of this implementation will be bounded by how fast I can traverse the whole active event FIFO. So here in this implementation, we additionally partition this FIFO to allow parallel access and comparison. So in this way, it results in throughput and resource trade-off in this implementation. On the software side, we define some modular software algorithm. The merge algorithm actually will decide to merge to AU when they are checking on potentially the same objects. So we use two different algorithms on the merge algorithm. The first one is the distance-based merging algorithm. It will merge when the distance of 2 AU is really small. And the ratio-based merging algorithm will merge if the overlap ratio of the two AUs is large enough. And similarly, the split algorithm will decide to split one AU into several AU if the active events collected by the AU falls into separated clusters. So basically we leverage different clustering algorithms for the split operation. So the first clustering algorithm is the hierarchy clustering algorithm, and also the second is the DB scan clustering algorithm. Finally, it goes to the results. We run our frameworks on 3 different data sets, the shape 6 DOF, inbound traffic, and outbound traffic. We evaluate our performance, the MOT performance using the HOTA matrix, a higher order matrix for evaluating multi-object checking. So this is a relatively new matrix in the computer vision community. Here shows this figure shows how we calculate this HOTA value. The HOTA accuracy can be decomposed into detection accuracy and association accuracy. So it calculates like this for each IOU threshold. The IOU means the overlap ratio between your proposed bounding box and the ground truth bounding box. For different IOU threshold, you calculate the detection accuracy and association accuracy under this threshold. Then after you obtain this curve, you do the integration of the curve to become the final accuracy results. In this slide, we show a very important resource accuracy trade-offs in our framework. Because our framework is targeted for multi-object tracking, and if we embed more AUs on hardware, it's very likely you can check more potential objects and result in higher accuracy. However, our hardware resource is constrained. We cannot embed it in finite number of AU on hardware. So that's also the reason why we do different optimization on different implementation of AU. So here in this plot, you can see that the tracking accuracy will increase as the maximum number of AU allowed it at the beginning, and then saturate at some points, because now the AU is enough to check all the objects in the dataset. And this is actually a dataset dependent parameters. In our final implementation, we devise 3 designs on 2 different edge platforms, the Ultra 96 and PINK-Z2. And we can see that for the same platform, the hash AMAP implementation can be much more resource efficient than the full AMAP implementation, while the FIFO-only implementation can achieve higher throughputs, up to 2 mega events per second. And all different implementations have different power consumptions, range from 2 watts, around 2 watts to 6 watts. And compare our framework to CPU, because all the AU are running in parallel, we achieve scalable performance compared with CPU up to 34 times speed up and 25 times more power efficient than CPU. Here shows an interesting trade-off in hash table design, because if we use a larger hash table in a hash AMAP implementation, it's likely we will come with fewer hash collision and a higher accuracy. However, it will also result in more memory consumptions on the hash table implementation. So this figure actually shows this trade-offs in accuracy and the hash table configuration. And in our final implementation, we choose the 8,000 times 1 slot hash table configuration without any accuracy loss. Last but not least, we find out that this hardware software architecture actually brings much room of tolerance in software latency. Because we decouple the hardware event processing and software high-level algorithms, actually the software is now not constrained by the conventional frame per second matrix to show the real-time performance. This is because our hardware is continuously checking events. So we no longer relies on the frame per second concept to show that our system can run in real time. Here shows the latency of our high-level merge and split algorithm versus the maximum number of AU deployed. We can see that the latency increased dramatically. However, we also find out that because our hardware is continuously checking events, we actually don't need to do merge and split like per frames, which means it's 25 hertz in every 25 times merge and split per second. So in this way, our hardware and software have a decomposed processing rate, and which is one of the advantage in our framework. In conclusion, the remote architecture is a highly modular, a flexible, scalable hardware software architecture that decouple the low-level event processing and high-level vision decision algorithms. And it achieved real-time and low-power performance on the edge devices. Thank you.